Hello, my name is Ramya, and today I'm going to be teaching you all about cladistics. So there are some key definitions that are important to know before diving into cladistic analysis, the first of which is a phylogenetic tree. A phylogenetic tree is a hypothetical tree based on a genetic backing. In lecture, we saw phylogenetic trees of primates based off of albumin protein data and DNA hybridization data. Next, it's important to distinguish phylogenetic trees from cladograms. Cladograms are ordinal, based off of common ancestry. They represent the most parsimonious tree created to accommodate a matrix of traits for a set of taxa. In cladograms, you can distinguish apomorphies or derived traits and plesiomorphies or ancestral traits. Within apomorphies and plesiomorphies, you have these terms: a topomorphy, just one taxa has a derived trait; synapomorphy, many taxa share a derived trait; and on a similar key, symplesiomorphy, many taxa share an ancestral trait. The best way to understand these terms and make it more than just words on a page is by applying it to an example. So here we have the key species in English letters, and we're going to try to apply these four main terms. First, a monophyletic group. This entire clade is a monophyletic group if we say our common ancestor is this node right here. That's because this monophyletic group includes all descendants of your common ancestor. Let's say this trait, this purple trait right here, is that of feathers. All the species after this common ancestor has feathers. Feathers can be called a plesiomorphic trait. It is present because the common ancestor had it. More specifically, it's a symplesiomorphy that A, B, C, D, E, and F have it. It's a shared ancestral trait. The word homology actually fits very nicely into this example because homology means similar characteristics due to common ancestor. And that's exactly what we see here. All of these species have feathers because the common ancestor has feathers. But let's say there's some mutation that happens right here. And instead of feathers, B derives a trait of hair. Here, hair becomes an apomorphy. It's a derived trait that's not in your common ancestor. More specifically, the hair that's in B is an example of an autapomorphy. There's only one taxa in this entire clade that has the derived trait. Let's say instead of just B having that trait of hair, though, all of these species have the trait of hair. We would still call it an apomorphy. It's a derived trait because your common ancestor right here had feathers and not hair. But now it's a synapomorphy. It's a shared derived trait. Every single red dot you see here means that that taxa or that species has that trait of hair. Additionally, if I were to say my common ancestor is still this purple node right here, and I was to circle all of this red section, I would call that a paraphyletic group. It is all connected because of this one common ancestor, but I don't include all of the descendants of the common ancestor. I critically exclude species A. But if I were to say my common ancestor is this red node, and I still circled that same section, now it becomes a monophyletic group. This example demonstrates how critical it is that you understand that all of these terms are in relation to your common ancestor. Now let's take the same example and say just B and F have hair. If I was to just circle B and F, that would be an example of a polyphyletic group. B and F are very distantly related. There is no specific direct common ancestor that links them unless you go really far back and you say down here, which is quite a stretch. Regardless, because B and F have hair, which isn't present in our common ancestor, which I'm keeping as this purple node, it's still an apomorphy. It's still a derived trait. But now this derived trait is also an example of a homoplasy instead of a homology like we see right here. It's a homoplasy because the least amount of events that could have occurred are two independent events that led B and F to have hair due to potentially, and most likely, similar selective pressures in their environment. If I was to say this is homology, then I would expect that the hair mutation and trait showed itself over here, which means C, D, E lost the trait, B and F gained it. It's way too many events. It's not parsimonious. And once again, with cladistic creations, we always want to make sure we're creating the most parsimonious outcome. Now, this example right here is more similar to what you might see if you're provided a matrix of traits and asked to create a cladogram on your own. Here, I've labeled the species A through J. Echinoderm is A, saber-toothed tiger is J, and I've also labeled the 15 derived traits from endoskeleton to long canine teeth. It's a tip that you can also use to make your cladograms less overwhelming and easier to write out without all the words jumbling up together. I want to clarify that each of the blue circles mean that it's a distinct derived trait. So it's like 1, 2, 3, 4. But colored circles that are colored the same are the same derived trait. For example, these two green circles represent trait 8, which is for scales. We have gone through a lot already in this presentation, so I wanted to use this slide as an opportunity to test your skills and see what you've learned. So let's get started with a question. If I include all of the species in this diagram included under the heart node, would you say it's a monophyletic group, a polyphyletic group, or a paraphyletic group? If you said monophyletic group, you would be correct, and that is because I'm including all of the descendants of my common ancestors within that grouping. Also, just for clarification, here OG means outgroup. I just included it because I wanted to show a taxa that didn't have any of our derived traits. All right, let us move on to our next question. Let me say now that my common ancestor is right here. It's this cloud. And this common ancestor has lungs, and it passes its lungs trait down to all of these species right here. Would you say having lungs is a type of plesiomorphy or type of apomorphy? If you said plesiomorphy, you would be correct. And that's because here I changed what the common ancestor was. I told you that the common ancestor is the cloud. So having lungs, just like the common ancestor, is an example of a shared ancestral trait. Thus, more specifically, it's a symplesiomorphy. If I was to change it up and say the heart is the common ancestor, now having lungs becomes a derived trait because lungs evolved somewhere over here. So now instead of being a symplesiomorphy, it's a synapomorphy. It's a shared derived trait instead of a shared ancestral trait. Another question, what is an example of an apomorphy in this diagram if I keep the heart node? Every single oval is an example of a derived trait or an apomorphy because it wasn't present in the common ancestor, but over time it became present in the species, in the descendants that followed. Thank you so much for listening to my presentation on cladistic analysis, and I hope you've learned a little bit more about how to apply all of these various terms to the cladograms that you see and that you use. If you would like to learn more about how to create a cladogram and understand it, you can also look at this amazing instructional video. And also right here, I have provided some relevant LS7B collaborative learning session documents that you can practice on your own time. All right, that's all from me. Thank you so much. Bye-bye.